All right, let's jump right into this explainer. Whether you're chatting with ChatGPT, Gemini, Claude, or Grok, there's a fundamental truth we often just completely overlook. Every single one of those tools runs on physical hardware. And no, it's not the processor sitting inside your laptop right now. It's something completely different. Today, we're decoding the incredible, highly specialized hardware that is secretly powering the entire artificial intelligence revolution.
We've got a lot of complex ground to cover today, but we're going to break this all down step by step. Here's our roadmap. 1. The infrastructure boom. 2. Why NVIDIA dominates. 3. The custom innovators. 4. The software moat. 5. The on-device revolution. And finally, 6. The ultimate energy bottleneck. Okay, part 1. The AI infrastructure boom. To really wrap our heads around the sheer scale of this technological arms race, we first have to follow the money. We need to look at the unprecedented amount of capital changing hands just to build the foundation of this AI era. Over the last 3 years alone, a staggering $2 trillion has poured into AI infrastructure. $2 trillion. And the vast majority of that mountain of cash isn't going to software subscriptions or fancy office buildings. No, it's going directly to physical chips. The tech giants are basically buying up silicon as fast as it can possibly be manufactured. And this perfectly illustrates who the undisputed reigning champion is right now. Just 3 years ago, NVIDIA posted $26 billion in annual revenue. Fast forward to last year, boom, $197 billion. That astronomical leap isn't just a good business quarter. That is literally the fastest hardware revenue growth in human history. They went from being known mostly for video game graphics cards to becoming the most valuable chip company on Earth. So, part 2. Why exactly does NVIDIA dominate? Why did NVIDIA's specific type of chip become the gold standard for AI? Why couldn't we just use the regular processors we've been building for decades? Well, it all comes down to architecture. A regular CPU, the kind inside your computer, is built for complex logic executed in sequence. Think of it like having 16 incredibly smart professors solving highly complicated word problems one at a time. But AI training? It doesn't need complicated logic. A neural network fundamentally relies on simple, repetitive math, specifically matrix multiplication, run billions of times. A GPU is built for that exact simple, repetitive, parallel math. NVIDIA's H100 chip has over 16,000 simpler cores doing the exact same operations simultaneously. It's like having 16,000 elementary schoolers doing basic addition all at once. And it turns out the math behind rendering lighting in a video game and the math behind AI are exactly the same kind of math.
But here's a catch that most people miss. Raw processor speed, it actually isn't the real bottleneck anymore. The true obsession of every chip designer today is memory bandwidth. Picture a swimming pool that you need to fill with water. You basically have two options. Option 1 is a garden hose, a slow, steady trickle. Option 2 is a massive, incredibly wide pipe. That is the exact difference between regular memory and the memory inside a modern AI chip. To understand why having that wide pipe matters so much, just look at the Llama 3 model, one of the biggest public AI models out there. It weighs 140 gigabytes. Every single time that language model generates a single word, just one token, the chip has to load that entire massive 140 gigabyte weight from memory. If you doubled the processor's calculation speed tomorrow, it literally wouldn't help at all, because it would still just be sitting there waiting for the data to arrive. The true limit today is how fast you can move data, not how fast you can compute it. Moving right along to part 3, the custom innovators. Now, because NVIDIA's chips are so incredibly expensive, with single H100 selling for over $40,000 at peak demand, and because they're built for general-purpose AI, several massive tech giants have stepped up to build their own custom silicon. Google actually started building their tensor processing units, or TPUs, back in 2015 to handle their own massive internal scale, and they've improved them 1,500 times over 9 generations. Then you have Grok, who designed the language processing unit. Grok was actually founded by one of the original Google TPU architects, and their chip abandons flexibility entirely. It puts the memory directly on the processor die itself, meaning there's absolutely zero latency waiting for data to travel across a bus. And let me tell you, the results of that hyper-specialization are wild. While standard cloud GPUs will give you about 20 to 50 tokens per second when generating text, Grok's specialized architecture delivers a blistering 300 tokens per second. That's a massive 6 to 15 times improvement in response speed, designed purely for enterprise use cases where every single millisecond literally matters to the bottom line. However, there's always a catch, right? The trade-off for that blistering speed is astronomical cost. Because Grok places memory directly on the chip, there isn't much of it. Running a 70 billion parameter model requires stringing together, or sharding across, roughly 576 Grok chips. That creates an $11 million hardware cost just for a single serving cluster. It proves that these custom chips aren't really for general workloads. They're meant for highly specific, high-paying niches.
Which brings us to part 4, the software moat. So if other companies like Google, Grok, Amazon with their Trainium chips, and Microsoft with their Maya chips can all build specialized silicon to avoid NVIDIA's crazy margins, why does NVIDIA still control 80 to 90% of the market? Well, it certainly isn't just about the hardware specs. Take AMD, for example. On paper, AMD's Instinct MI300X chip completely crushes NVIDIA's H100. It boasts 192 gigabytes of memory compared to NVIDIA's 80, and 5.3 terabytes per second of bandwidth compared to NVIDIA's 3.35. That massive memory advantage means you can serve open source models with far fewer chips, which seriously lowers costs.
But having the best metal isn't enough. Just look at Intel. They had every advantage: billions in cash, global foundries, deep data center relationships. They even spent $2 billion acquiring Habana Labs. Their Gaudi 3 chip had highly competitive specs. But by late 2024, Intel had to admit they were going to miss out on $500 million in revenues simply because their software ecosystem wasn't ready for customers. Actually, they ended up canceling the next generation chip before it even reached users. Raw specs are meaningless without a frictionless way to actually use them. So the crucial point boils down to this. Hardware without a software ecosystem is just expensive metal. NVIDIA's real dominance does not come from having a single good chip. It comes from a 15-year head start built in CUDA. Released way back in 2006, CUDA is a software platform baked into how every single AI developer actually works, learns, and builds. It's 15 years of libraries, tutorials, and deep optimizations. It is a moat made entirely of software, and you simply cannot buy your way out of that overnight. All right, part 5, the on-device revolution. While these massive cloud wars are raging between NVIDIA, AMD, and the major tech giants, there is a quiet, completely different revolution happening right inside your pocket. Every iPhone since 2017 has actually had a dedicated AI chip called the Neural Engine. Back in 2017, the A11 chip delivered 0.6 teraflops. Fast forward to the M4 chip today, it delivers 38 teraflops. That is a 60-fold increase in power in just 7 years, all running off a tiny battery. This is what allows features like Face ID, live text, and on-device Apple Intelligence to run privately without your data ever having to touch a cloud server. And everyone else in the consumer space is racing to catch up. We are seeing incredible neural processing units, or NPUs, just flooding the PC market. Qualcomm, Intel, and AMD are all pushing chips that deliver between 45 and 50 tera operations per second. In fact, Microsoft is now demanding a minimum of 40 teraops for any PC to even qualify as a Copilot Plus device. The gap between a massive data center and the device sitting in your hand is shrinking every single year. Finally, part 6, the ultimate energy bottleneck. But if we zoom back out to those massive supercomputers training the next generation of trillion-parameter models, we hit a massive physical plot twist that changes the entire trajectory of this industry. 3 years ago, the constraint was simple. We just didn't have enough chips. The factories couldn't print them fast enough. But today, the constraint has shifted. We're facing an entirely different, much more physical wall that money alone cannot easily bypass. NVIDIA's newest Blackwell architecture is an absolute beast. A single rack of their new chips draws 120 kilowatts of power. That's about 6 times what a normal server rack consumes. It requires entirely new electrical and liquid cooling infrastructure. A 100,000 GPU cluster now requires the exact same electricity as an entire small city. NVIDIA's CEO has explicitly stated they could ship more chips tomorrow if the power grid could actually absorb them. The AI infrastructure story has officially become an energy story. It's gotten to the point where Microsoft is literally funding the restart of the 3 Mile Island nuclear plant just to keep their AI servers running. I mean, think about that. And this perfectly illustrates where we're heading. We are entering an era of extremes. On one side, we have colossal centralized clusters consuming literal nuclear-level energy to train the absolute largest foundational models. And on the exact opposite side, we have increasingly capable, highly efficient silicon running complex models locally and privately, right in the palm of our hands. Every major technological era was defined by a specific piece of hardware.
The PC era was built on Intel. The mobile era was built on ARM. The AI era? It's going to run on whatever architecture survives this crucible of bandwidth limits, software moats, and massive energy constraints. Right now, as dominant as NVIDIA is, nobody has definitively won the long game yet. And that leaves us with a fascinating question. As energy grids strain and our pocket computers get exponentially stronger, who do you think will ultimately take the crown? I hope you keep exploring this fascinating battleground with us, and I'll catch you on the next explainer.